Hello guys, and welcome back to another video. Today we're talking about circular motion, and here we have our particle, our point particle that is moving along the circle, and we want to describe how this motion occurs, what is going on here. So we have our circle, and there are two ways to describe it. We could use polar coordinates or Cartesian coordinates. So let's start with polar coordinates because there are some advantages of polar coordinates and some advantages of Cartesian coordinates. So I'm going to show you what I'm talking about. So we put our axis, our x-axis here, and we want to draw the radius starting from the center because it's always better to pick the easiest position for the coordinate system to describe what is going on, so the equations are simpler. So we just put the origin at the center of the circle because now this arrow here has a constant length because this is the radius of the circle and the radius of the circle is constant. Now let's say that this particle is moving with a velocity v in this counterclockwise direction. So how can we describe its position in terms of polar coordinates? We need two parameters because we're working in two dimensions. So one is the radius and the other is this angle here with the x-axis. So in polar coordinates, we have that our position is a function of the radius that is constant and of the angle theta. Now, there's a good way to express this. We can simply put r in the direction of the radius. So this is just a scalar multiple of this unit vector here. It says, okay, you have to go the distance r in this direction, the direction of the radius, and then we have our theta parameter. In what direction? In the direction the particle is moving. So if theta increases in this direction, this is our unit vector for the theta angle. Now, it might seem counterintuitive to have a unit vector for an angle, but that's just a convenient way to represent what's going on in Cartesian, in polar coordinates. Now, the easy part is that the equation is simple. Obviously, theta changes as a function of time, and we're going to see how it changes later on. But as you can see in polar coordinates, it's simple. But when we take its derivative to find the velocity and then the acceleration, those two unit vectors, as you can see, move along the curve. So we have to find a way to differentiate them, and we're not going to do it. We're going to use the Cartesian way to express this motion using the parameter theta and r, obviously. Now, we know we have to put our y-axis. This is our y-axis, and we only need to find the x and y coordinates of this point particle. So that's our x coordinate. This is our y coordinate. And as you can see, the x coordinates is just r times the cosine of theta, and the y coordinate is r sine of theta. So we can simply, describe this motion using two unit vectors, one going along the y-axis that we call j hat, and one going along the x-axis, I hat. We use unit vectors because that's a convenient way, because we have our position vector now as a function of theta, which equals r cosine theta in the x direction and r sine theta in the y direction, and this is equal to r cosine theta in the x direction, so times the I hat unit vector plus r times sine of theta in the y direction. I prefer writing vectors in this way, and I think it's better sometimes when working with more difficult scenarios, but this is also a convenient way using a column vector. Now, that's what is going on here. We want to find what the velocity is, so let's differentiate this vector. So we have dr by dt, because we're differentiating with respect to time. We want to know how r changes as time goes on. So just differentiate this. We have r cosine theta, r is just a constant. So we have r, the derivative of cosine is minus sine, so minus sine of theta times the derivative of what we have in here. The derivative of theta with respect to time, we call it omega, and it's the angular velocity, so how the angle changes, how fast the angle changes. We have to do the same thing here. The derivative of sine is cosine, so we have plus, in the I direction, plus r cosine theta times omega in the j direction. So this is our velocity. Now, before going on and calculating what the acceleration is, let's spend 2 seconds on this equation here. We want to know what is this equation telling us. So firstly, let's find what is the direction of this vector acceleration, because it's very important to know that. So let me draw a new circle here. The y-axis, the x-axis, our position vector, our point particle. Now, let's think about it in this way, and then we're also going to use this equation here. At a slightly later time, we have this new vector of the position because it's moving in this way, the point particle. If we take the difference of these two, this is delta r, and what dr by dt, that is the velocity, equals to is just the limit as delta t goes to 0, let's call it delta t of delta r by delta t by definition. So delta t is just a number, a scalar that multiplies delta r, so the direction should be perpendicular to this position vector, because as this red position vector approaches the first one, they should get perpendicular. And we can see that from the coordinates here, because if we have r cosine theta here we have a minus r sine theta, r cosine theta. I think it's better to see it from this, because this is the definition of velocity, and it's easier to see. Now, the acceleration is even better because we need to take the derivative of this equation here. So let's do that. And we have our vector acceleration. This is the acceleration, and this is a very important step. Derivative of sine is cosine, then we have to multiply by omega, the derivative of theta, so we have minus r omega squared. We have cosine theta in the I direction, plus, minus, because the derivative of cosine is minus sine, minus r omega squared sine of theta in the j direction. Now we can factor out this minus omega squared, and what we get is r cosine theta I plus r sine theta j, but this is the same as r of theta, so let's do that. This equals 2 minus omega squared r of theta, or just r is a function of theta and time, but let's write it in this way. So as you can see, the acceleration points in the opposite direction of r, because if this is r, we have a scalar multiple, so it just scales the vector, and we have a minus sign, so it points in this direction here. So this is a centripetal acceleration directed towards the center of our circle. And a cool thing to note here is that if this omega is constant, obviously we're treating it constant because when we differentiated here, we didn't account for how it changes. So we're assuming that the angular velocity, so the velocity, the magnitude of the velocity is constant. What's the magnitude of the velocity? The magnitude of this vector here is simply equal to the square root of the square root of this plus the square root of this. Sine squared plus cosine squared equals 1. So we have r times omega. And obviously if omega is constant, v is also constant. And we can rewrite our position vector since omega is constant as omega t, so we get it as a function, how theta changes as a function of time. Now, what is really important here is the acceleration, because as you can see, even though the magnitude of the velocity is constant, because the angular velocity is constant and the radius is constant, there's still an acceleration. We're accelerating. Even though it seems we're going with a constant velocity, we're accelerating. We're accelerating because velocity is not a scalar, it's a vector, so it also has a direction. If you change it, if its magnitude is kept constant, but its direction changes, then we have a change in velocity because velocity is vector. Or in other words, even though is not changing in magnitude, along the x-axis is constantly changing, and along the y-axis is constantly changing. So this is what's important about circular motion, and this turns out to be important for every motion we try to describe. So in the next video, I think we're going to start to look at dynamics and probably something more about kinematics, because all of what we've done so far is very important for the next videos. So I hope you enjoyed this video, and as always, remember to subscribe to my channel, leave a thumbs up and share this video with your friends. As always, until next time, bye.